Hello my friends and welcome to my channel. I'm playing with some vintage junk again. Someone just wanted to throw that away. That's an electricity counter, a watt-hour meter, and it's made in the year 1959. It's a Swiss product. That's a model you found, or you probably still find everywhere. So if they are in good shape, they still count kilowatt hours as in the old days. And it's so simple how it works that it has to be explained, because yeah, it has almost nothing inside. So let's see what's inside. So first here is a cover for all the electrical contacts, and there is already a schematic diagram. So I hope we can see that. It has some sort of coil and another coil, 90 degrees to that coil. That's not resistors, that's the terminal blocks here. And there is another device with a switch and a motor. But I don't have that, that's an additional device, so we only have this. One coil, two coils and a third coil, and all the rest is just jumpers and wiring. So, how do you count watt hours or kilowatt hours with only 2 or 3 coils? Whoops. It doesn't work if you drop your tools. So that's one screw, and that's the other screw, and that's how we get in. So, what can we see? We see a mirror-like disc. We see one coil, or well, it's a double coil with very thick wires. And we see another coil here with obviously very thin wires. And then we see here a third coil that is connected with these orange wires to that block. And that block is somehow connected to the connection block down here, where all the in and output wires from the house installation, from the house wiring go. So we also see an arrow and a hole where we can see the disc, and the disc has a black marking here, so that makes it a bit easier to see that it turns. And you can also count the revolutions, just in case you don't trust the counter up here, which is a purely mechanical thing. You see there is a worm gear here on this disc axis, then a big plastic wheel down here. That brown thing goes to that wheel, goes to that wheel, and that already drives the 2 counters here. So first of all, why do we have 2 counters? Maybe you can see that arrow here that flips up and down when I move the instrument. Normally this arrow here is flipped by this electromagnet here, and that simply indicates which of the 2 counters is actually counting. And we have a N and a H. That means normal tariff, normal price, and high tariff, high price. So what does that mean? There are times in a day when electricity is more expensive or times when it is cheaper. So for example, at midday, when all people went home cooking their meals on an electric stove, you get the high price because this is meant to drive people to save a little bit of energy in that time of the day. And on the other hand, during the night, when most industry is powered down and all the lights are off, there is too much electricity, so you get it for a lower price. So this is switched by signals that are sent through the electric grid, and these signals are recognized by this second device here, and that simply switches that selector here. And it's also, of course, a mechanical switch that changes the drive from one counter to the other and back. So that's why we have two counters, for the high price kilowatt hours and for the low price. So you see there is nothing on the high price and a lot of the normal price. The reason is this was privately used just to count electricity usage, and they didn't have this second device that actually changed the counter here. Okay, so we have two electromagnets, one on the bottom, one on the top. We have this contraption here that looks like an old horseshoe magnet, more or less, with a very small gap where the disc goes through. There is also some kind of adjustment contraption here, so it is meant to slide your flat screwdriver here and move the entire thing back and forth, so you can move it that way. There are also three adjustment screws for the position here, so that the disc here runs exactly in the center of that magnet. Yes, it is a magnet. My screwdriver sticks to it quite strong. Now the big question is, this disc here looks like an aluminium disc. So why is it driven by electromagnets? Well, let's find out what happens here. Well, you have probably already seen that trick with the magnet and the copper pipe that has nothing inside. If you drop the magnet, it takes a while until it falls out on the other side. So it seems someone or something is holding it. And just to show that I'm not cheating, well, kind of strange phenomenon, right? So you may say, that's a copper tube, that's not an aluminium disc. Okay, that's an aluminium sheet. It's not a disc, it's just a thick, massive sheet. And we probably have the same. It's a little bit difficult with a round magnet, but I think you can see it. It also slows down quite a bit. And you may also say, yes, it's nice that an aluminium or a copper tube or a flat piece slows down a magnet, but how does a magnet drive a piece of aluminium? Okay, let's take a smaller piece of aluminium. That's a small heatsink. It would also work with that one, but that's a little bit too heavy for that. So let's see what happens. So as you know, aluminium is not magnetic, but if I lift that up quickly, something strange happens. It seems that aluminium is magnetic. See that? I can almost lift it or flip it over. And that's not because it's sticky, it's absolutely clean. No, we could also do this without touching it. That was touching it, okay. But it also moves when I move the magnet. And the faster I move the magnet, the more this follows or is even attracted to it. You see that? It comes closer. And I'm not touching it. It's just attracted by the magnet somehow. The answer to the question, how is this possible, is simply eddy currents. Now, my magnet has a magnetic field around it. And, of course, my piece of aluminium here has no magnetic field when my magnet is far away. When my magnet is directly on the aluminium, the magnetic field just goes through it and nothing else happens. But if I move that in any direction, we also move the magnetic field here around. And the moving magnetic field means we have a changing magnetic field. And the changing magnetic field in a conductor induces currents. And those currents go like that, in circles. Or maybe in another shape, depends on the shape of the magnetic field of my magnet here, but in this case they go in circles. So we have electricity. I is the letter for current. So there are electrons going around here inside this metal piece. Electrons that move inside a metal piece are also generating a magnetic field. So from the right-hand rule, if the current goes like that, the magnetic field goes like that. So I did not define which way this thing here goes, but I assume it will go like that. So we have an attraction. Yeah, I think that's what happens here. We have an attraction. But only if when I move the magnet. And the magnet is stationary, no attraction at all, except when I remove it quite quickly, it lifts the aluminium. Is that true? Same direction means attraction. Yes. So let's say that's a north pole, that's a south pole, that's a north pole. Yes, that attracts each other. The same is true, of course, for a tube, only that the currents are then around that magnet, because the tube looks like that. But the magnetic field is also, well, it should be in the other direction, because it breaks down, it breaks the fall of the magnet. Okay, I'm a little bit confused right now, but I think you get the idea. We are inducing currents. Currents are generating magnetic fields, and they interact with the magnet. Well then, let's see how that works when current is applied. oops, sorry, shake the camera. So I have this very special connector here. It's a connector that goes into a main socket. There is another socket. And the clue is here that 2 of the 3 connectors go straight through. And the third phase connector goes through that wire and comes back to the other side. And also earth and neutral are also linked to this side. So at the end we have 3 wires here. Yes, we don't have the earth connector on this side because we don't need that, but we have neutral, input phase and output phase here. Okay, let's just plug that in, and you see nothing happens, of course, because we are not drawing any power. So let's plug in my little super precision load resistor here, aka a hairdryer. Goes in here, and this one has a power of 1800 watts, so that should make that little disc spin. Let me zoom in a little bit so you can see the disc. Let's see. On the first stage here, there's not much doing. Okay, I think you can see clearly, there's the mark. And on full power it spins quite fast. Maybe we can see it a little bit clearer right now. Okay, so this disc makes 1000 revolution per kilowatt hour. That means when we connect the load with 1 kilowatt and let it run for 1 hour, this disc makes 1000 revolutions per hour. The maximum load here is 7.5 amps at 220 volts. So that's 1650 watts. So with my 1800 watt hairdryer, I'm already slightly overloading it. That's why it shows us the unhappy face here. Now I notice that there is a little bit a problem. First of all, this disc here is very wobbly. You can see it here. I think that shouldn't be so. So there is an adjustment screw, but when I adjust it a little bit tighter, it doesn't turn at all. So I think we probably need a little cleaning and a drop of oil to make that work again. Okay, let's do that. Well then, so for an old device, we also need old tools like this knot holder pliers. This is exactly made to grip small nuts like that and to turn it gently. So let's unscrew that. Oh, it's already sticking somehow, so that's a bad sign. So what's inside here? Looks more complicated than I expected. Okay, so there is something spring-loaded. Can we take that further apart? No, I don't think so. So it's a bit strange that it's only like a little tube where this tip here rides inside. So probably there is even a part missing. Alright, so I found that this part can be disassembled a little bit further, because you can unscrew that cap here, and this reveals a spring, and I can already tell you this is quite sticky here. That grease or oil that has been inside feels a little bit like honey, and that's certainly not what it should be. So there is this little tube here that is inside a bigger ferrule, and I think here is where the turning action actually happens. So the tip of the axle of the aluminium disc goes inside here, like that one, and then it turns with this little piece here together. So the actual bearing is inside this tube here, and I think that just needs a little bit of fresh oil and a cleaning. Just a little bit of alcohol and a small brush. By the way, what you hear from the outside, it's not ghosts or ghouls, it's just teenagers. They are playing around and being a little bit silly. Okay, I'm not entirely sure how much I should tighten this screw here, so I took exactly the moment when it touches the axis, the shaft, I'm sorry, axis is something else. Okay, the cap got loose again. So I think it's already a bit better, but we also have a bearing on the top side here. And I probably have to do the same, but first I will release that again a little bit. Let's see how that works. The right screwdriver. Ooh, that's interesting. A super small needle bearing. How does that work? I hope I don't destroy anything. So at least it has the same sticky grease, so it gets a cleaning. With the faceplate removed and also this cover here from the coil removed, we can actually take this disc out. And I'm already surprised again to see that the wheels here with the numbers they are not made of plastic, they are actually made of aluminium. So the full mechanical part here is made of metal. And I also see there's some kind, it looks like a small differential gear. That's interesting. It's almost like Swiss clockwork. Okay, that is driving one side, and I think when that flips over, yeah, it drives the other side. Can you see that? So now it drives the right side here, and with the switch it drives the left side. That's great. I didn't expect a mechanical device like that. And all the parts are made of aluminium. So they are certainly not CNC milled. I think they are cast and then probably engraved on a engraving machine, and of course painted and everything. Yeah, that's nice. So let's see how that bearing here works with the needle. So the needle goes in here. It's a little bit tolerance, and there is a spring wound around here. Don't know what that is good for. Maybe to catch some oil or something that could eventually drip down. Let's clean that. Yeah, there's a tiny little hole inside this shaft. Don't know if you can see that. In the video I can see it with my eye. So let's try to clean that out, because that's all full with some old sticky oil. So I hope that's good enough. Okay. And we place a drop of fresh oil inside. Yeah, that should do the trick. Let's see if it feels differently. So there's still a little bit of wobble here, but I think it's only, the bearing is only between that small hole inside and the needle itself. And then gravitation pulls the disc down to the other bearing here. Let's clean that tip also. Okay. So yeah, that's how it's spinning. Okay, let me put that together. Well, before I put everything together, let's find out how these coils could eventually work. So as I said, we have a large coil here with thin wires, and we have a smaller coil here with thick wires. So the thin wire coil here is parallel across neutral and phase, so it's directly on 220 volts. And it works all the time because voltage is always there. The other coil is in series with the phase input and output, so that means a magnetic field is only generated when current flows. So if there is no current, only voltage, nothing happens, disc will not turn. But if current does also flow, Then we have power, current times voltage. And if the power is over a certain time, it counts on and on and on. Now that means one coil alone cannot do anything. So the voltage coil alone doesn't spin the disk. And of course the current coil alone cannot do that either. So there must be some phase shift between the two coils, the two magnetic fields. And of course, the more current we draw, the stronger that field here gets. This one is constant as long as the mains voltage is constant, and that's pretty much all the time. So the current here creates a magnetic field. The voltage coil also creates a magnetic field, and when these two fields play together, the disk starts spinning. Now, don't ask me exactly how that works. I'm pretty sure there is a lot of documentation around. What I think is interesting is that everything on this meter is adjustable. So for example, we have this device here that can be moved with a screwdriver like that, and I'm pretty sure that somehow influences the balance between the two magnetic fields, or even the balance of this, I call it the voltage coil, let's call that the current coil. So that probably only influences the voltage coil. Well, we could see what happens if I move that around. Maybe the disk starts spinning by itself without current. Then another thing that can be adjusted is this one here. That's where the upper bearing for the shaft is. This is an eccentric hole, so the position of the upper bearing can be rotated to any direction. That makes sure that the shaft is perpendicular to, well, to gravity. I also showed the adjustment of this magnet here, and I think the purpose of this magnet is to adjust the speed of the disk, because this acts like a brake. So it's a permanent magnet where an aluminum disc spins inside that breaks that disc. It's a disc brake. And here you can adjust it to go more in or more out. So this will probably break the disc harder, and the other side, I need a bigger screwdriver. The other side will probably make it run slower, because it's more towards the center of the disk, where the disk is a little bit slower than on the outer edge. What else can we adjust? Okay, we can adjust the position of the magnet, like this way, or even this way, so that the disk fits exactly into this groove here. Any more adjustments? We already had that. Then also interesting, there is a magnetic shield around this coil here. And I think that shield probably has two functions. First of all, to shield the magnetic field from that coil from the disk, so that nothing influences that disk. But it could also be that someone with a magnet here could theoretically flip that mechanism. Where is it? Oh, here. So that's the upright position. He could flip that mechanism and make, for example, when the electricity price is high, could flip it to the low price with an external magnet. So that kind of tinkering or faking the counter was quite popular. Another method to make it count a little bit less is to put a strong magnet here or on the other side. That's also possible, because a DC magnetic field will slow down the disc, as this magnet here already does. So if you make that magnet stronger, your disc will turn slower and it wouldn't count all the electricity you used. This is of course highly illegal, and I wouldn't recommend to do that anyway, but that's an old trick and all the electricians know that, and that only works with these mechanical devices. There are also these strange energy saving devices that more or less consist of only a big capacitor, which is connected somewhere in your mains supply, and that should effectively save energy. But there is the trick with an electric. So this electromechanic counter here or device, it only works perfect when there is a ohms load, ohmic load on the grid. So a resistor, for example, a heater, anything with coils or capacitors, they shift the phase between voltage and current. And if for some reason you shift the voltage and current extremely, for example, you have a purely capacitive load, this thing stops working. So when current and voltage has a phase shift of 90 degrees, which is normally not the case when you have a resistive load, that's the word, resistive load. But the more inductive or capacitive load you have, the less accurate this thing will be. So that means if you hook a big capacitor to your mains, you probably produce a phase shift, and a mechanical voltage, current, power meter will probably not work correctly and read less than you actually used. So in fact, these devices do not save power. In fact, the capacitor that is connected to the mains it draws power, it consumes power by itself, but it could theoretically trick out one of these mechanical power meters. If you have an electronic power meter is complete, then this capacitor stuff is completely useless, because they also measure the phase shift and they calculate everything with their microprocessors, and yeah, that's how that works. And this happens when you mix up input and output. You see the disc runs backward. You see the arrow here, it should go that way, but now it goes that way. And it actually also counts in reverse. So that's another trick how to reduce your energy bill. But the cover here has a seal around here, so you cannot break that, or you cannot open that without breaking the seal. And your electrician, or the guy who reads that counter, that meter, will know that you have done something. So let's put it in the right direction, input and output. So we don't want any reverse current count here. Okay, let's try it again. Yep. And this meter is definitely not made to lie on a table. It's made to hang on a wall like that. Okay. And that's what I thought. You already see it spinning backward a little bit. And that's not only gravity, that's certainly because I moved the... It also humes right now. Yeah. So I brought it out of balance with my little movement of that trick there. So the question is, how can I adjust that now for the disc to stand still? So that's very tricky. So it seems the disc can actually spin if there is no current. So at the moment there is no current, it's only voltage, and it actually spins backward. Now let's see how I can get in there to adjust that. Maybe like so. No, that's a little bit, oh, from that side it's probably a bit easier. I just hope that works without sparking and without killing myself. That would certainly bring me a lot of YouTube views, but I don't really like that. So let's move that a little bit. How's that? If I move that a little bit more, discs should start. Yes, now it turns in the other direction. Can you see it here? So that has to be, well, it's not spinning freely, but it moves. So we have to bring that to a position where the disc is actually not spinning at all, which is not very easy if you don't have the right tool. So how about that? Yeah, it's still moving. No, forward. It's vibrating quite a bit. Maybe I have to adjust that bearing a little bit. No, I can't. So, how is it? Yeah, it's still spinning a little bit, but I think I will adjust that later. You certainly have understood the principle. Okay, that's it. Mechanical electricity counter. Thanks for watching.